There is one question about Venus that scientists still cannot answer with complete certainty. Not why the planet is so hot. Not why its atmosphere is thick enough to crush almost anything we have ever landed there. Not even why its surface is hidden beneath an endless blanket of cloud. Those are the easy questions. The difficult question comes much earlier. Was Venus always doomed? Or did something happen that slowly erased every path that could have led it toward becoming another Earth? At first glance, the question hardly seems worth asking. Look at Venus today. The surface is hot enough to melt lead. The pressure is more than 90 times greater than the air pressing down on you right now. Clouds of sulfuric acid surround the entire planet. Nothing about that world suggests it was ever anything else. For a long time, that seemed like the simplest answer. Venus was simply born different. End of story. But over the past several decades, that explanation has become increasingly difficult to defend. Not because anyone found ancient oceans. Not because a spacecraft uncovered some forgotten landscape beneath the clouds. Nothing that dramatic ever happened. Instead, the planet began revealing its history in much quieter ways. A strange chemical fingerprint trapped high in its atmosphere. Radar images that exposed a surface unlike Earth's. Measurements that refused to fit the picture of a planet that had always been beyond saving. Individually, none of those discoveries rewrote the history of Venus. Together, they began telling a very different story. One in which Earth's closest planetary twin did not lose everything in a single catastrophe. It lost something else first. Then something else. And then another chance that never came back. Each change made the next one harder to escape. Each step quietly narrowed the number of possible futures. Until one day, there was only one future left. Today, Venus is often called Earth's evil twin. That description is accurate. But it also hides the real mystery. Twins are supposed to grow together. Earth and Venus did the opposite. They began remarkably alike. Yet somewhere in their shared history, one world kept every mechanism that allowed it to remain habitable. The other began losing them, one after another, until the planet we see today became inevitable. The question is no longer whether Venus is a hostile world. We already know that. The question is how a planet so much like Earth gradually reached a point from which it could never return. Two planets. Almost the same size. Almost the same mass. Built from nearly the same material, in the same young solar system. If you looked only at those numbers, you would expect them to follow remarkably similar paths. One became the only world we know that can support life. The other became a place where a spacecraft struggles to survive for even a few hours. At first, scientists assume the answer must lie in the obvious difference. Venus simply orbits closer to the Sun. It receives nearly twice as much sunlight as Earth. Perhaps that alone was enough. It was an elegant explanation. And for a while, it seemed like the only one anyone needed. But the more researchers measured Venus, the less comfortable that answer became. Because being closer to the Sun explains how a planet can become hotter. It does not explain why two worlds that began so similarly ended so completely differently. Something else had happened. The first real clue wasn't hidden beneath the clouds. It was hiding inside them. High above the surface, spacecraft sampled the atmosphere and found something that looked almost insignificant. A different form of hydrogen. One that is just slightly heavier than the kind found in ordinary water. By itself, that measurement meant very little. Hydrogen exists throughout the solar system. Finding it on Venus was never the surprise. The surprise appeared only after scientists compared one kind of hydrogen with the other. The heavier form was far more common than anyone expected. Not by a few percent, by roughly 150 times more than the ratio found in Earth's oceans. That imbalance should not exist by accident. Heavy hydrogen escapes a planet much more slowly than ordinary hydrogen. If the lighter form is missing while the heavier form remains behind, something must have carried enormous amounts of ordinary hydrogen away into space over an immense span of time. The atmosphere had preserved the aftermath, like footprints left long after the traveler had disappeared. One measurement could not tell scientists exactly how much water Venus once possessed. It still cannot. That boundary remains one of the biggest uncertainties in reconstructing the planet's early history. But the measurement did something just as important. It destroyed the idea that Venus had always been as dry as it is today. For the first time, the planet's atmosphere stopped looking like a permanent condition. It began to look like the survivor of a much longer story. And if Venus had once held far more water than it does now, another question quietly replaced the first. Where did all of it go? The obvious answer seems simple. The Sun. Venus circles the Sun much closer than Earth does, receiving almost twice as much sunlight. For decades, that appeared to explain everything. A little more heat, a little more evaporation, a planet that simply started on the wrong side of a line. But the chemistry refused to leave the story that simple. Water doesn't disappear because a planet becomes warm. It has to leave. Somehow, every molecule must be broken apart, every hydrogen atom given a path into space, and every opportunity to rebuild that water must disappear. That doesn't happen overnight. It unfolds over immense stretches of time. As Venus grew warmer, more water evaporated into the atmosphere. Higher and higher it drifted, until sunlight itself began pulling the molecules apart. Each molecule became two different stories: hydrogen and oxygen. The hydrogen was the easy one. It was the lightest element in the universe. Without the protection of a global magnetic field like Earth's, Venus offered little resistance as those tiny atoms escaped into space. Not in one great burst, not in one catastrophic event. Year after year, million after million, the planet leaked, almost too slowly to notice. If you could have watched Venus from space, nothing dramatic would have happened. No exploding oceans. No giant clouds racing into the darkness. Only an invisible trickle of hydrogen drifting away, one atom at a time. Any single moment would have looked insignificant. Billions of years later, the result was anything but. The water that disappeared carried something else away with it. Not just hydrogen. It carried away one of the planet's most important ways of keeping itself stable. As long as liquid water exists on a rocky world, rain falls, rocks weather. Carbon dioxide is gradually pulled from the atmosphere and locked into stone. Earth has been performing that quiet exchange for hundreds of millions of years. Most of us never notice it, because when it works, almost nothing appears to happen. On Venus, that quiet process slowly came to an end. As surface water disappeared, rain disappeared with it. Without rain, rocks could no longer trap carbon dioxide in the same way. Yet volcanoes did not stop releasing it. The atmosphere kept receiving carbon dioxide. The planet gradually lost the easiest way to remove it: Nothing changed all at once. That was the danger. Each step still looked survivable. Each step only made the next one a little more difficult to reverse. By the time the atmosphere began transforming into the crushing blanket we see today, Venus had already surrendered one of the most powerful systems that allows a rocky planet to regulate its own climate. Even then, Venus had not yet become the world we know today. That is what makes its history so unsettling. Losing water did not destroy the planet. It removed the mechanism that had been quietly protecting it. From that point forward, every volcanic eruption tipped the balance a little further. Volcanoes continued releasing carbon dioxide, just as they had for millions of years. On Earth, much of that gas eventually finds its way back into rocks through the slow cycle of rain, rivers, and weathering. On Venus, there was nowhere for it to go. The atmosphere simply kept growing thicker. A little thicker. Then thicker still. More carbon dioxide trapped more heat. More heat prevented water from returning. With less water, even less carbon dioxide could be removed. The planet had entered a loop that fed itself. No single step was extraordinary. Together, they became almost impossible to interrupt. By now, the familiar image of Venus begins to change. It is no longer just a planet with an extreme atmosphere. It is a planet whose own systems had started working against one another. Every process that once helped maintain balance had either weakened or disappeared. Every process that remained pushed the planet in the same direction. The atmosphere remembers part of that history. The surface remembers another. When radar finally pierced the thick clouds, scientists expected to find a landscape broken into enormous moving plates like Earth's. Instead, they found something remarkably different. Impact craters lay scattered across the planet with surprising uniformity. They were not concentrated in ancient regions while absent from younger ones. They were spread almost everywhere. Just as striking, those craters showed almost no sign that the crust had been pulled apart, folded, or recycled, the way Earth's surface is constantly reshaped. The planet looked locked, as though its outer shell had become one enormous, continuous lid. Exactly how Venus reached that state is still being studied. The leading explanation points back to the same missing ingredient: water. On Earth, water does more than fill oceans. It also weakens rocks deep within the crust, allowing sections of the surface to sink, recycle, and slowly carry heat away from the planet's interior. Take enough of that water away, and the crust becomes stronger, stiffer, far less willing to bend. Over immense spans of time, the engine that continually rebuilds Earth's surface may simply fail to keep operating. Venus appears to preserve the result. Not proof beyond every doubt, but an independent line of evidence pointing toward the same history. The atmosphere says the planet lost enormous amounts of water. The surface says it became a fundamentally different kind of world. Two completely different records, both telling remarkably similar stories. By this point, it becomes tempting to look for the moment everything was lost. One disaster, one eruption, one final turning point that sealed Venus's fate forever. The planet offers no such moment. Instead, every line of evidence points towards something far more gradual. Recovery did not disappear in a single day. It became less likely every time another planetary system stopped working. The atmosphere trapped more heat. The surface remained dry. Volcanoes continued feeding carbon dioxide into the sky. The crust grew increasingly resistant to the kind of recycling that constantly renews Earth's surface. Each process strengthened the next. Each one quietly closed another door. Eventually, the question was no longer whether Venus could return to its earlier state. The question was whether the planet still possessed any mechanism capable of pushing back at all. So far, nothing suggests that it did. Seen separately, none of these observations explains Venus. The atmosphere cannot. The surface cannot. The chemistry cannot. The radar maps cannot. Only when they are placed together does the picture begin to sharpen. A planet receiving more sunlight loses increasing amounts of water. Less water means less hydrogen remains bound to the planet. Without liquid water, carbon dioxide is no longer locked away inside rocks. More carbon dioxide traps more heat. More heat makes water even less likely to survive. A drier planet leaves behind a stronger, less mobile crust. That crust struggles to recycle itself the way Earth's does. Heat escaping from the interior changes. Volcanic gases continue entering the atmosphere. The cycle tightens again. No single step doomed Venus. The system did. That is why scientists cannot point to one exact date when the planet crossed the point of no return. The evidence does not reveal a single irreversible moment. It reveals a sequence. One threshold leading quietly into the next. Some transitions may have taken hundreds of millions of years. Others perhaps much longer. The exact timeline is still debated. The overall direction is not. Every independent measurement points toward the same conclusion. Venus did not suddenly become impossible to save. It slowly stopped giving itself the chance. And by the time every surviving clue was finally written into the atmosphere, the rocks, and the shape of the planet itself, there may have been no path back at all. Now, place Earth and Venus side by side one last time. The comparison looks almost unfair. One world is covered by oceans. Its atmosphere allows liquid water to exist. Its crust breaks, sinks, and renews itself over and over again. Carbon moves from the sky into the rocks, then back again, in a cycle that has been quietly stabilizing the planet for hundreds of millions of years. The other world kept almost none of those systems. Its water disappeared. Its atmosphere became overwhelmingly carbon dioxide. Its surface locked into a single shell. The same planet that once resembled Earth now preserves almost every consequence of losing the mechanisms that keep a rocky world in balance. That comparison is no longer just about two neighboring planets. It has become physical evidence that nearly identical beginnings do not guarantee similar futures. The most remarkable part is that scientists did not arrive at this picture through a single discovery. No spacecraft found an ancient shoreline. No probe uncovered the exact moment Venus changed forever. Instead, the history emerged piece by piece. A chemical fingerprint in the atmosphere. Radar maps beneath the clouds. Measurements of pressure. Measurements of composition. Observations made decades apart by different missions. Each answered only a small question. Together, they described one continuous history. Some details remain uncertain. Scientists still debate how long liquid water may have survived on early Venus. They continue to investigate whether the planet's surface was reshaped by one enormous episode of volcanism or by a much slower process spread across vast spans of time. Future missions may narrow those uncertainties. They may even rewrite parts of the timeline. But none of those questions erase the broader picture that has already emerged. The atmosphere still carries the chemical signature of immense water loss. The surface still preserves a planet unlike Earth's. The physics of carbon dioxide still explains why heat continued to accumulate. And together, those independent observations continue pointing toward the same reconstruction. Venus was not born as the world we see today. It became this world through a chain of changes that reinforced one another until recovery itself disappeared. The brightest planet in our night sky is no longer simply Earth's twin. It is the surviving record of how two worlds that began astonishingly alike gradually separated, one irreversible step at a time.